All right, let's talk about a word you've probably heard thrown around a lot: entropy. It's one of those ideas that's absolutely central to, well, pretty much everything in physics and chemistry. But man, it can be a real head-scratcher. Don't worry though. By the time we're done here, you're gonna see it in a completely new light.
You ever notice how some things in life just only go one way? It feels like they're on a one-way street, right? And they can't turn back. Well, it turns out that's not just a feeling. It's not a coincidence. There's a super deep, fundamental reason for it, and we are about to unpack it.
I mean, seriously, think about it. When's the last time you saw your coffee unmix itself, right? With the cream just neatly pulling itself back out into a little blob, or a puddle on the sidewalk suddenly deciding to turn back into perfect ice cubes on a hot day? Never. It just doesn't happen. And that, right there, is entropy in action.
Okay, so if you've heard anything about entropy, it was probably this definition, right? Entropy is disorder. Entropy is chaos. You know, a messy room has high entropy, a clean one has low entropy. It's a really easy way to think about it. But, and this is a big but, it's also kind of wrong. Or at least, it's a very misleading shortcut.
So let's test that whole disorder idea right now. Take a look here. You've got a cup full of crushed ice, a total jumble of different shapes and sizes. Looks pretty disordered, yeah? And next to it, you have a glass of perfectly still, room temperature water. So, which one looks more chaotic to you? Which one has more disorder?
I'm willing to bet most of you are pointing at the ice. And yeah, it totally looks messier. But here's the twist. The water actually has higher entropy. Whoa, right? And that little fact right there tells us everything we need to know. The whole disorder analogy, it's broken. It just doesn't work. So we need a better way, a much better way to think about this.
All right, so let's just toss that whole idea of chaos and disorder out the window for a bit. We're going to find a way to get to the real heart of what entropy is.
And what's that better way? Well, it all comes down to one word: probability. Yep, that's it. Forget messy rooms. The real secret to understanding entropy is just good old-fashioned statistics. Now, I know that might sound a little intimidating maybe, but stick with me because it is literally the key that unlocks this whole thing.
So, to really get a feel for this, we're going to play a little game. We're going to build a super simple model, a little toy universe basically. And by figuring out the rules of this tiny game, we're going to see how this massive cosmic idea of entropy actually works.
Okay, so here's our setup. Picture two tiny solids. We'll call them solid A and solid B. And let's say each one is made up of just 6, let's call them slots or bonds. These little bonds are where energy can be stored. And the energy itself comes in these little indivisible chunks we call quanta. So the more energy quanta a solid is holding, the hotter it is. That's it. Simple rules, right? All right, now for the most important word in this whole explainer: microstate. Don't let it scare you. All a microstate is one single specific arrangement of those energy chunks in all the available slots. Think of it like a photograph, a single snapshot showing exactly which chunk of energy is in which slot at one exact moment. So let's play. Let's say we have 8 of those little energy chunks to play with, and we decide to put 6 of them in solid A, making it the hot one, and the other 2 in solid B, the cold one. The big question is, how many different snapshots, how many unique microstates can we get with that exact 6-to-2 split? Get this, the answer is 9,702. Isn't that wild? In our tiny little toy system, there are almost 10,000 ways to arrange the energy to get the exact same temperature difference.
And this chart is where it all clicks. It shows what happens with all the possible ways we can split up our 8 energy chunks. We could cram all 8 into one solid, right? That's the 8-0 split, our 6-2 split. But look what happens when we spread the energy out as evenly as possible, a 4-4 split. The number of possible microstates, the number of ways to arrange the energy, just explodes. It's way, way bigger than any other configuration. So if the universe is just randomly trying out all these different arrangements, which one do you think it's most likely to land on? Yeah, the one with the most options.
And that brings us to our brand new, much better definition of entropy. So forget disorder. Just think of it this way. Low entropy is concentrated energy. High entropy is spread out energy. That is it. A state of high entropy isn't messier, it's just more probable. There are just way more ways for the universe to be in that state.
Okay, that's cool for a static picture, for a single snapshot in time. But in the real world, things are always moving, always changing. So what happens when we put our little model into motion? Let's see.
Right. So in reality, energy isn't just sitting still. It's constantly vibrating, jiggling, jumping from one of those little slots to the one next to it. It's restless. And what that means is our system is constantly, randomly shuffling itself into new microstates, one after another, millions of times a second.
So let's go back to our starting point. 6 energy chunks in A, 2 in B. If we let the system jiggle just once, where's it most likely to go? Well, if you run the numbers, there's a 21% chance it'll land in that super probable, spread out 4-4 state. That makes sense, but check this out. There's also a 13% chance it just stays where it is. And even crazier, there's an 8% chance that the hot object gets even hotter. It's totally possible, purely based on random chance. And that should make you stop and think, right? If there's an 8% chance, a not insignificant chance, for the hot thing to get hotter, why don't we ever see that in real life? Why doesn't your lukewarm coffee ever just decide to start boiling on its own? What's going on here? The answer, my friends, is all about scale. Our little model was a toy, a simplification. The magic happens when we start scaling things up. So instead of 6 bonds and 8 energy units, let's just multiply by 1,000. Let's imagine a system with 6,000 bonds and 8,000 energy units. Now keep in mind, that is still unbelievably tiny compared to, say, a cup of coffee. But just watch what this little jump in scale does to the math. Remember that 8% chance for the hot thing to get hotter? Well, in our new, slightly bigger system, that chance plummets. It becomes, well, look at that number. 0 point, a whole lot of zeros, 1%. It's a number so small it basically doesn't mean anything. For all intents and purposes, it's 0. It's not going to happen.
And that is the punchline. That's the whole secret. Something that was just a little bit unlikely in a tiny system becomes absurdly, ridiculously, impossibly improbable in a real-world system with trillions upon trillions of atoms. There's no magical force that says heat must flow from hot to cold. It's just statistics. The alternative is so mind-bogglingly unlikely that you could wait for the entire age of the universe and you would never, ever see it happen. Not once.
So what does all this mean? It means this statistical certainty, this avalanche of probability, is so powerful that it actually gives time a direction. It's why we experience the past, present, and future in a straight line. It's what scientists call the arrow of time. And now we can finally answer those first questions. Why does ice melt? Why does cream mix? It's not because of some weird force. It's just because the universe is constantly, randomly stumbling around, and the state where the energy is all spread out, melted water, mixed coffee, is just so much more probable. The system is just falling into its most likely state. Which, of course, leaves us with a huge final question to chew on. If the entire universe is a system, and it's always moving toward a state of higher entropy, always spreading its energy out more and more, where does that road lead? What's the ultimate fate of the universe when all its energy is perfectly, completely, and evenly spread out?